have time to do the applied problems. So here is the deal. I'm going to look over the applied problems this weekend, okay? I'll give you what you got, and then if you would like to try and get in the cup, I will come up with some sort of plan and opportunity for you to do that, okay? But it's not going to be in class today because we are on our time crunch and we need to make sure that we stay focused and get done what we need to get done. Does that sound okay? So I'll give you feedback about that on Monday, and we'll move on from there. Question?
I just want to let you know I'm going to be gone.
Okay, thanks for letting me know.
Yeah.
I will too.
You leave at 2 o'clock.
Oh, I'll be gone too.
Everybody's leaving us. Oh well.
I'll be gone.
We'll record it. All right, friends. Shh. So let's talk about our plan, and then you can figure out how that's going to impact your life. So today I've got a couple of little announcements. Don't let me forget those. Jacob, don't let me forget that, okay? Little announcements after I go through kind of what our plan is. We're going to organize motion today because that seems like a thing to do because we've been doing a lot of stuff and I can't keep track of all of it. Then we're going to talk about angular momentum. We'll talk about it a little bit, and I'll give you some example problems to work. That's going to be the majority of our day. I did not get homework posted. I know that you're probably super excited to do homework during 7th hour, and if that's the case, I apologize, okay? Maybe you can do the homework that you haven't done yet. I don't know. But anyway, I'm not saying that's true, but I'm just saying, I will get homework posted for this section by 4:05 today, probably earlier, but I'm just going to give myself a little window of opportunity there. By the end of the day, by the time I go home today, you will have homework posted, and that will be all of the homework because we will have gone through everything from this unit. So just kind of to be aware of that and just to know where you're at in terms of everything we've done in this unit. Woo! It's been a little while. It's been almost not quite a month, but we talked about Newton's first law. We talked about center of gravity, excuse me. I don't know what I was talking about. Center of mass, center of gravity, thank you. So we'll just call it Mavity, it works. Equilibrium, rotational kinematics, Newton's second law, kinetic energy. We're going to do angular momentum today. We're going to review, so these dates are not quite right anymore because we got off from my absence on Wednesday. The plan is to go over homework, to review, to do whatever cleanup you need in class on Monday, okay? Absolutely, for those of you that will not be here, I'll record it. It will be as if you were here, okay? But if there are things that you would like to go over, if there are questions that you have, please send me an email. And you can either say, hey, can you go through this in class when you record it? Or can you just explain it to me? And I can absolutely do that too, okay? I will also be here before school on Monday and on Tuesday, so I can go through stuff with you then as well. My plan is to do our quiz test. It's really a test. I stole this actually, honestly, from my physics kids who are taking just a quiz. But I'll say the unit, what is this, unit 7? I'll put a question mark because I can't remember for sure. Unit 7 test. I won't give you the unit 7 test if that's the next one because that wouldn't be right. Okay, but I'll give you the test on Tuesday is my plan. Does that seem all right so far?
Sure.
Okay. I feel like I saw a hand. Is that your hand? Yeah.
I typed my lab thing. So
Yes.
I shared it with you.
Yes.
I didn't turn it in, so I just
That's
think
fine.
you got it.
Thanks. I am sure that I did if you shared it with me.
So you want to
Yes.
share it with me now?
Which is a friendly reminder to everyone, right? Thank you for saying that. Your rotational acceleration conclusion evaluation is due by 11:59 tonight. Okay. So if you wrote it up by hand, you can stick it in my basket. That's awesome. If you didn't, or you've already shared it with me, that's great too. Just make me a part of your life. That's what I want, just to be able to read your conclusion evaluation. Okay. I will work on grading those, but yes, if you just share it with me, I'm sure I will have gotten it. It'll be great.
Right.
Okay. Anything else? Questions for the good of the order right now? Okay. 2 really quick announcement things because I just got this in an email and I wanted to make sure that you were all aware that Monday is PJ Day because I didn't want anybody to miss out on that opportunity if that's something you love. I know, right? So,
What if Tuesday brings?
friends, we've got a lot to do and we're going to get through what we can get through. So, I just want you to take that to heart today. Okay, thank you. But anyway, I wanted to make sure you knew that you could wear pajamas on Monday. I mean, not that, I don't know, whatever. Anyway, the other announcement that I had logistically has to do with There's a physics and astronomy. The physics and astronomy department at the University of Iowa is hosting their spring demo show, which is free and open to the public. Sometimes people are like, oh, that kind of sounds nerdy and lame. But I will tell you that they put on an extremely good show, okay? The guy who does all of their demos is a friend of mine. I've known him for a long time, and he's kind of like a physics magician, and he's kind of amazing. So anyway, I would strongly recommend, if you are free Friday, March 15th, so that's next Friday. It's the Friday that starts spring break, okay? 7 to 8, Van Allen Hall is the one that's kind of on the north side of the Ped Mall area. Strongly recommend it. It'll be a really good show. Bring your friends that aren't physicists because they'll enjoy it too. It's not like you have to understand physics. They're not going to put you on the spot. You're just going to watch, and it will be great. So anyway, strongly recommend that because it's fun. Okay. All right. So the last few units, kind of when we hit a big point of like, let's keep ourselves organized, I've given you a chart, and I'm going to give you a chart today as well to kind of keep track of what we've been doing. So this is what it looks like, and I'll bring it around to you so you can start filling it in. We're not going to take a ton of time, but I do want you to use this now to get your head around what we've been doing for the last month. I think that's all right. So friends, I want to make sure that this is productive time. I'm going to give you just a few minutes to fill out as much of this as you can. Absolutely use your notes if you need them. This is not a quiz. It's an opportunity to organize your ideas and to organize what you know. Okay, we kind of started making things like this in our notes in the last few days, but just an opportunity to get it organized. So go ahead and get started with this. It's going to lead us to the last row, and the last row is where we're going to do our notes today. So don't worry about not knowing the last row because we haven't done that one yet. Okay? I'll give you just a couple minutes to get this started. Don't want to spend too much of our time just filling this out. So I'm just going to throw my solutions for the right-hand side column. The left-hand side one should be fairly straightforward, but just to make sure that we're all on the same page here, again, I'm glad I heard at least a couple people say that this was a good refresher, good review, so I'm hoping that that's the case. That's why I put it together. Rotational displacement is theta, measured in radians. Rotational velocity is omega, is delta theta over delta t, radians per second. Acceleration is alpha, change in omega over t. Sorry, that got a little bit messy. Radians per second squared. Is that stuff all making sense? Yeah. Okay. It's all just translating information from our translational motion into rotational. Okay. Again, if you want a reminder of how this all fits, you can think about that carousel ride and that horse and the tiger or whatever it was that were on that carousel. Who is going to win? It depends on what you're talking about, right? The kinematics equations are just the translation or the rotational equivalent to the translational, okay? On your equation sheet, just to be aware, it does list a couple of them. It doesn't include the squared one, okay? But it's all just that translated stuff, so you can figure it out. Cause of acceleration, what causes angular acceleration? It's a net torque, right? That's the thing that causes acceleration. Just like what's the cause of translational acceleration? A net force, right? Yeah, and you might want to throw in there just this is the first time I've used this chart, so I'm going to kind of add a couple things in here. I'm going to say that equilibrium requires... Yes, it's true. I know you don't have this. I'm writing it in here on the side, and you can write it on the side too if you want. F net to be 0 and torque net to be 0. Right? So you can just throw that in there if you want. Again, you don't have to. This is not required. I'm not going to collect this. This is for you to help you get this all in your brain. Okay? The thing that causes resistance to acceleration is, in terms of translational, it would be mass, right? And in terms of rotational acceleration, we're talking about this I thing. What is, yep, so mass is the resistance to translational acceleration. Resistance to rotational acceleration has to do with mass, but it also has to do with the radius, the placement of that mass relative to the axis of rotation. This thing is called, you might want to just write it down so you don't forget, moment of inertia, right? Okay. The units for moment of inertia, hold on, let me just throw that in there and then we'll be all over it. What are the units for moment of inertia? Kilogram meter squared, right? Isaac, what was your question, hon?
So the problems that you had yesterday on the board for the circles and the radians and stuff.
Yeah.
Are those going to be on the test?
So you're talking about, hold on, let me see if I can find that little thing. Hold on. Oh wait, where did it go? Yeah. I know, I'm just trying to find it up here. I can't find it for sure. But yes, I know what you're talking about, like all of those equations. So let me make sure that everybody hears this so you don't have to ask later. The purple sheet that had the different moments of inertia for the sphere and for the ring and for the disc, you absolutely do not have to have those memorized, okay? And if you would need it on a test, they would give it to you. Does that make sense? So most of the time, as I've said to you before, most of the time on an AP Physics exam, they're not going to have you calculate anything, let alone the moment of inertia of a disc, right? Or whatever. They're going to want you, they'll be like, here's a disc and here's a ring. Which one's going to get to the bottom first? And why? Right? That's what you need to be able to answer. Okay? That's the kind of stuff. But if you were in a situation where you needed to that equation, they would either give it to you or it would be a situation where you need to be cognizant of the fact that it has a different moment of inertia, and maybe you're graphing things to figure out the moment of inertia. Do you know what I'm saying? Like that I would totally not put past the AP people, right? They would totally do that. They would give you the opportunity to figure it out that way. Yeah.
Can I describe that?
Yeah.
Remember, this F-net is a unit.
F-net?
Yeah. Does it have units?
It's just a force, so it'd be a newtons. All right, Newton's first and second law. So I would say if torque net is 0, alpha is 0, right? That's Newton's first law officially, but I just call this first and second law because it's the same thing. If torque net isn't 0, alpha isn't 0. Again, this is the first time I've made this chart. I'm going to make a change to it when I get home or, next period or whatever. And that would be to say just, oh, by the way, here is the statement of Newton's first and second law, right? Alpha equals torque net over I. I might throw one in over here that says A is equal to F net over M. Okay. Rotational kinetic energy is 1/2 I omega squared. And the units for that? Joules. Joules. Just like always. Okay. Now, that's okay. You're good. I just want to make sure I'm not. You may notice that there's some space at the bottom of this paper. We need to do some teasing out to figure out what's going on with momentum. So I'm just going to put my notes right here. But if you want to put these on separate paper, you're absolutely welcome to do that as well. Okay. But we need to figure out momentum because we haven't done that one yet. So the first little piece that we might want to talk about here is the impulse momentum theorem. You remember the impulse momentum theorem? You're like, yes, I sure do, Miss K. So if you were thinking about the impulse momentum theorem, you might be thinking about the fact that F net times time, a net force acting over a time. What does a net force acting over a time result in, friends?
A force.
What? A force acting over a time results in an impulse, and an impulse is a change in momentum, right? Does that sound familiar? I probably wouldn't actually put this in the box. I don't really know why I did, and I apologize for that if that was weird. Okay? So I would here, I'm going to move it. You can move yours too.
Well, that trick is
Right? Delta P. Rho is density. We're not going there today. Right, so you may notice that I spelled momentum with an M today. And that was not on accident. I know, right? It's kind of weird. There's no momentum because this momentum is spelled with a P. This one isn't. Just wait for it. I know, right? Here we go. So, I'm going to write this down one more time. Just say F net times T is equal to M delta V. So that's really what we're talking about generally when we're talking about a change in momentum is a change in velocity to some sort of mass. Okay? This thing right here is momentum. Okay? We can say a very similar thing for rotation. What would be the rotational equivalent to, I'm going to use this statement right here. What's the rotational equivalent to force? Torque. The net torque. What's the rotational equivalent for time? Time, don't be tricked, right? Just making sure we're paying attention. Okay? That's equal to, we're just going to keep translating because we've already established all of this up here. What's the rotational equivalent to mass? I, moment of inertia, right? And finally, the rotational equivalent to the change in velocity is going to be change in omega. Oh, yeah? All right. This thing right here is angular momentum. It's angular momentum. Okay? Angular momentum is represented by the letter L.
There it is. I saw it. I was like,
You saw that it was there, right?
yep, saw
Yeah.
the L.
Yeah. Right? Big L! Yeah! I put a big L in the middle.
Yeah, that's what I saw.
I tried that once. I tried to see if that would catch on, and it never really did. Momentum. It doesn't work. So L. Change in angular momentum is equal to I delta omega. Okay? This is the definition of angular momentum. Okay? We're going to take this one step further. We're going to remind ourselves, we're going back to the translational stuff. Okay? We're going to remind ourselves of the whole story here. We said before with the momentum that if no F net is applied, in a closed system, what has to be true about the change in momentum? The change in momentum is 0. Okay? This statement right here is conservation of momentum. Okay? Remember, this was the thing that we did with our little carts, our carts on the track. We did all of those analyses. Okay? We can say a similar or parallel statement for rotation. We can say then that if no what? Net torque is applied, in a closed system, what do we know? Change in L is 0. Okay? This is a statement of conservation of angular momentum. You like low momentum? We can write that down. Does that make you happier? See, now I want to write it LP, though. That's my problem. So that I'm like, I don't even know.
You can just insert an apostrophe.
Seems kind of like French, right? Like, I don't know.
You just insert
Yeah.
an apostrophe between the L.
Oh, that would be cute.
The moment.
Okay. We're adopting a new phrase today. All right. We're going to take it one more time, one more step. Okay? So now, if the momentum is 0, the change in momentum is 0, we're going back to our translational. If the change in momentum is 0, then we can say, I need more colors here, we'll do this one, okay? That the initial momentum of the system has to equal the final momentum of the system. And generally, when we're talking about a conservation of momentum, translational momentum system, we talk about like two carts knocking into each other, right? Because if you have just one cart moving, it's really not very exciting. It's true, but it's not very exciting. So you've got like M1V1 plus M2V2 is M1V1 plus M1V1. Is that sounding familiar to you? Okay. When we do conservation of angular momentum, generally it's just going to be the momentum of the thing at the beginning and the momentum of the thing at the end. Okay? It's usually just one object that's changing something about it that causes something else to change. So if we do this, then we're going to say that L initial equals L final. Let's see what that L contains. It contains I and omega. Hold on, is that okay? Hold on just a second. Okay. So that means that you've got I initial, omega initial has to equal I final, omega final. Okay. Again, this usually just has to do with one object. Sometimes it's more than one object. You have seen this a lot, I am sure, without maybe even realizing it. Question, comment, whatever, go ahead.
Can the rotational momentum get transferred into translational momentum, like if a bowling ball hits the pins?
For sure. Yes. So but then you're dealing with outside forces maybe perhaps, right? So it depends on what you call your system. It gets a little more complicated. I will say that in the problems that we're going to do, we're probably not going to do that. Does that make sense? So we like to put translational and rotational kinetic energy together because they're kind of interesting together. But generally, we don't include both in terms of moment. Okay, so you've seen this before. Where have you seen this before?
Conservation.
I'm just going to walk away from this because I don't really know how to respond to it.
Yeah.
Where have you seen this before? You can say a snowball.
Oh, it was.
I'm thinking, you guys remember what my very, very favorite,
Hey, Rob.
my very favorite frog is? No, my very, very, very favorite Olympic sport, thank you, is ice dancing. Now, ice dancing, again, not so great, but figure skating, pretty fantastic. And I don't know if you've ever watched figure skating, but there are lots of components to a great figure skating routine. There's a lot of jumping, and again, if you've watched it carefully, they do a lot of like the biggest jumps at the beginning, right? Why do they do the biggest jumps at the beginning and not towards the end? Yeah, it's higher, right? You're like, I'm ready to go. You jump, you do like triple whatever, and throw people and whatever, right? What do they do at the very end of ice skating routines? They do the spin. You with me? Yeah? Who's going to do it? I feel like I want to pick on Elizabeth, but I'm not sure she wants to spin. Do you want to spin?
Elizabeth Chen knows how to dance.
I can do it.
You want to spin?
Wait, I'm listening.
Elizabeth Chen knows how to dance.
I know.
Irish dance on it.
I think you fundamentally misunderstand.
I just want you to stand on there. Okay.
I can sit.
Are you okay with that? Yeah.
Like, move
So
your
it
leg
spins.
higher
Is that
first.
okay? Like you're gonna spin? Yeah?
That's
That's great. All right, it's gonna get better.
Do what you
Maybe it like hold on like this.
T-pose.
T-pose.
That's what she's gonna do. You okay with that? So I can get you going?
Yes.
Okay. You are such a good sport. I just want to say thank you right now. All right, friends. She's gonna put her arms out, and as she puts her arms out, I just want you to observe. Because no, stop. Because we need to be done with that. Because I need you to just focus on what's going on here. So if she's just standing there, she's got mass. Would you agree?
Yeah.
And as I spin her, you can just leave your arms there. As I spin her, she's got moment of inertia. Would you agree?
Yeah.
Yeah, because she's got mass, and that mass is related and associated with an axis of rotation. The axis of rotation is like zoop right there. Yeah? Life is okay? Okay. Now she puts her arms out, and I happen to give her, so you can put them, there you go. You're such a good sport. Awesome. So she's got them out there. What has changed? Has her mass changed?
No.
No, but what has changed?
Moment of inertia.
Her moment of inertia has changed, right? So now I'm going to be an outside torque. I'm going to give you some outside torque. I'm going to get you to spin. Okay. Are you okay with that?
Yeah, let's go.
Okay. All right. Here we go. Now, so you're just going to spin. And then, whenever you want, you can pull your arms in. With me there. After I've pushed you a little bit. Here we go. So I'm going to get you going.
That's how you go.
Oh, yeah.
All right. Pull your arms in. Woo! Did you see that?
You got it.
Okay. We'll do it again. Because this thing is not super stable. So you did a great job. You ready to do it one more time? Okay.
Focus on your center
All right.
of gravity.
Thank you, Henry. Arms out. All right, here we go. So think about this in terms of what's going on here. So at first, I'm applying an outside torque, right? A force a certain distance away. But once I'm done with that, then she's just rotating. And now no net torque is applied to the system. She changes her moment of inertia. You with me there? Not changing the mass, but changing the radius. What happens when she has her arms out here? Is her moment of inertia bigger or smaller than when they're in? It's bigger, right? Because the radius is bigger. So she's got a big moment of inertia and a fairly low angular velocity. As soon as she pulls her arms in, the moment of inertia, come on, bing. The moment of inertia is down, but what happens to that angular velocity? It's going to go up. With me there? There you go again. You're fantastic. I appreciate it. Arms out.
T-pose.
Oh, yeah.
All right, here you go.
Order like Jeff with titanium.
Yeah. And then so we'll do it one more time. So now, and it's kind of fun. So this thing is not frictionless, right? So that's a truth. But you can still see this happening. Now, I want you next time. So you're gonna start out like this, pull it in, and then push them back out.
Ooh.
What do you think is gonna happen?
hard.
And shoot. Right, you can do it. Keep going over and over. Ready?
Oh,
Here we
you can
go.
go forever. It's infinite.
Here we go. Put your arms out. Whoa, and then pull them in.
Keep going.
Right? It just keeps going. Now again, there's lots of friction, so blah blah blah. But you get the idea? Okay. I'm gonna take this from you. If you guys want to try it later, you can, but I want to just make sure. Thank you so much. Give her a hand. Yay! That was fantastic. Woo! Look at that thing go. What's shaking? Yeah. Okay. Does this make sense? The concept here is not difficult, friends. Especially if you remember how to set this up. Initial and final and initial and final, initial and final. Okay? If you've got more than one thing that might be moving or might be related to this spinning, then you're just going to add all of the things at the beginning, all of the things at the end. As long as there's no outside torque, no change in angular momentum, right? Okay? Life is good? That's what you need to know. I'm going to give you some problems to work. Okay? I've got 4 of them here with answers on the side. You will notice this was totally on me when the sub gave you that set of problems that you may or may not have supposed to have been doing the first thing on Wednesday. The third one, the last problem, the one about Joey or something like that, that's actually an angular momentum problem. Yeah, so it's probably pretty hard, it was on me for screwing up, but also you shouldn't have been looking at it too long. Anyway, you can do it now. All right. So I'm going to give you these problems to work on. You've got, I don't know, 15 minutes to work. That's plenty of time. If